So welcome back, students. In this video we are going to see what happens when we connect capacitors in series and in parallel. Pretty much the same way you have already connected resistors in your 10th standard in series and parallel. What is going to happen when you have multiple capacitors and you connect them in series and parallel? So that is the focus of this video. So I told you that the symbol for capacitor is this is the symbol for capacitor, and then the unit of capacitance is farad, and then this capacitance depends purely on the geometry of the capacitor. So if you take a parallel plate capacitor, it's a special type of capacitor, right? It is given by epsilon naught A by D. Okay. And we also know that the field inside the capacitor is going to be equal to sigma by epsilon naught. And then the voltage is actually E into D, the distance of separation. And C, the basic definition for C, the capacitance, is simply Q by V. All this we have already covered. What we are going to do now is to take capacitors and then we will connect them in a series. Okay. So let's say I have a battery which gives me a voltage V. Let's say like this, voltage V, and I will connect this to a capacitor here. So this is C1, capacitance of this capacitor, and I'll take one more capacitor which is C2. Okay. And then I will probably take one more capacitor, C3. I can keep adding capacitors, but I'll just stop with 3 capacitors. This is C1, this is C2, this is C3. Now what is going to happen? And how will the voltage be distributed across the 3 capacitors, and what will happen to the charge, and what would be the ratio with which the voltages will be shared by the 3 capacitors, and what is going to be the effective capacitance. What do you mean by effective capacitance? Suppose I am going to replace the entire circuit with a single capacitor. Instead of 3 capacitors, I am going to have a single capacitor. And I am going to connect it to the battery with V. So what must be the capacitance? Here, that will get the same charge on the capacitors as this combination. And that is effective capacitance. Right? Okay. So this is actually going here. So the multiple capacitors, I should be able to replace the whole thing with a single capacitance. And that capacitance must draw the same amount of charge from the voltage, from the battery. Okay. So having stated this goal of ours, let us focus on what is going to happen here. Well, I have connected the positive terminal to this plate of the capacitor. So what will it do? Well, this is a metal, so this is a positive plate. Then pretty much the free electrons will run through this to the battery, right? Leaving this plate net positive. Because you have net positive there, let's say this is plus Q. It's net positive there. Then what will happen to this one, this plate? Well, notice that this plate is connected to this plate. So the whole thing will act as a single conductor. A single conductor in the presence of the field produced by this charge. And what will happen? The negative charges in this conductor will accumulate here. Okay? M minus Q. Because the negative charges accumulated here, because they are getting attracted by this thing, by this collection of charges, this part of that would become net positive. So what would the charge be here? Well, minus Q has gone there, so this must be plus Q. So notice then that the charge here plus Q is also the charge here plus Q. So both the capacitors will have the same charge. And because you have plus Q here, and now this acts as a single conductor, right? And you are going to keep the single conductor in the presence of this field. So what happens here is that negative charges will be attracted here, okay? Leaving this part positively charged. Well, so now you are going to get minus Q here, then you are going to get plus Q here. Then what happens here? Again, because of this field, negative charges will be attracted here. Anyway, because you have negative potential here, so it will repel the negative charges, and there is positive charge that will attract the negative charges. So the negative charges will accumulate here. Okay? So you get minus Q here. So notice, and these capacitors, I'll probably use a different color to denote them. So this is capacitor 1, okay, and this is capacitor 2, and this is capacitor 3, okay. So capacitor 1, capacitor 2, and capacitor 3. So you get plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. There. Okay, so this plus Q and this C1 will give rise to V1 here, right? Potential across this one. And the same plus Q and this C2 will give you potential V2 across this capacitor. And plus Q and then C3 combination will give you V3 here. Okay. So what do we do? What do we know? We know that this V1, V2 and V3 must be equal to V. So V must be equal to V1 plus V2 plus V3. So what is this V1? So V1 is going to be equal to Q by C. V is equal to Q by C, right? So this is going to be Q by C1, same charge. Here again V2 would be Q by C2, and then this would be Q by C3. So that gives you Q times 1 by C1 plus 1 by C2 plus 1 by C3. Okay, so this is V1 plus V2 plus V3, and that must be equal to V. Well, look at this circuit. So this is the equivalent circuit, right? So the same Q that you have here must be sitting here. That is when this becomes equivalent. So then you can replace the entire thing with just two plates with certain capacitance C. Then you have found the equivalent of this here. So if that is the case, what is V here? This V must be equal to Q by this effective capacitance C, right? So that is going to be Q by effective capacitance C. So you know that Q by effective capacitance C is equal to Q by C1 plus Q by C2 plus Q by C3. Okay? So the result is that Q by C is equal to Q times 1 by C1 plus 1 by C2 plus 1 by C3. and I can cancel Q and Q, then I get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is for 3 capacitors. I can generalize it for any number of capacitors, right? Suppose I have n number of capacitors connected in series in this circuit. Then the effective capacitance will have a relationship with all these capacitors like this. So the effective, if you have n capacitors, then I have 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 all the way plus 1 by Cn. Okay, so this would be the equation for capacitors connected in series. So this is capacitors in series. So for capacitors in series, you are going to get this relationship. Hope this is clear to you. Okay, the next topic is capacitors in parallel. This capacitors in parallel. So what happens when you connect a set of capacitors in parallel to each other? Okay, so let me take C1, C2 and C3, 3 capacitors. So C1, C2 and C3. Let us see what will happen now. So I will have the same potential here, V, and then I will connect C1 across it. This is a symbol, C1, and then I will also connect C2 across it, and I will also connect C3 across it. So what is my objective? I want to replace the entire thing, C1, C2, C3 with a single capacitor. The objective is I want to replace the entire thing with a single capacitor. So that should have the same amount of charge that came out of the battery. Okay. So this is the objective. So this is the objective. You're going to go from here to there. Let's see what is going to happen here. Okay, so these are parallel, so the voltage across them will be the same. So V1, if you call this as V1 voltage, and if this is V2, and then this is V3 voltage across this, I know that V1 is equal to V2 is equal to V3 is also equal to V. Okay, it's the same thing. Okay. What would be the charge here? The charge on this capacitor. We know that C is equal to Q by V, right? So V is the same for all of them, so I'm going to have V throughout. Okay, and just keep it here for the time being. Let's see. I'm going to V3 is equal to C. Okay. So V is equal to Q by C. So V is equal to this one, if you take that, Q1 by C1 plus this would be, so I will get Q1 here. Okay? That is it. So now again V can also be written as V2 is also equal to V, right? So it is equal to Q2 by C2. and then V can also be written as Q3 by C3. Okay, so think about it. Because capacitances are different, the charges on them will be different, so that V1, V will be the same across all the capacitors. So Q1 is sitting on this, Q2 is sitting on this, and Q3 is sitting on the third one. So all this came from the battery. So this will be plus again, be minus here, and this could be plus again, this could be minus, and this could be plus again, and this would be minus. Okay with that? So Q1, Q2, Q3, C1, C2, C3, it's going to be, so this is what you get. So you will have different charges. So we should be supplying Q1, we should also be supplying Q2, we should be supplying Q3 also. So we have supplied Q1 and Q2 and Q3. So what's the total charge out of this battery? So the total charge out of this battery is Q, which is equal to Q1 plus Q2 plus Q3. So that is the charge we should have here. So the battery would supply Q charge here. It will go and switch on that single capacitor, the effective capacitance. Okay. Because in reality, V supplies Q1 to this, Q2 to that, and then Q3 to that. So V supplies Q1 plus Q2, Q3. And here also we will supply Q that will sit on a single capacitor. So that is the equation there. Then what is Q? We know that C is equal to Q by V, so Q will be equal to CV. So I'll say Q is equal to this Q is equal to C into V. Okay? That's effective capacitance into the whole input voltage will be equal to the total charge there. Okay? And that is also equal to Q1. What is Q1? Q1 is going to be equal to V into C1. V into C1. What is Q2? V into C2. And what is Q3? V into C3. Okay, I can take V out, and that gives me C1 plus C2 plus C3 plus CV. So now I can cancel V's here. So I'll say C is actually equal to C1 plus C2 plus C3 in this case. So I've done that for 3 capacitors. If I have n capacitors, C will be equal to C1 plus C2 plus C3 plus Cl. Okay. So this is the net result when you have multiple capacitors in parallel. So you can see a certain difference between capacitors and then the resistors which you studied in your 10th standard. Okay. When you had resistors, if they were in series, you got R is equal to R1 plus R2 plus R3 plus Rn. This happened for series resistances. But in the case of capacitances, it happens when capacitors are connected in parallel. Likewise, when resistors were connected in parallel, then you got this 1 by R was equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on till you get 1 by Rn. Okay, that was the equation you had for resistors in parallel. But then you had something similar to capacitors, but capacitors were connected in series from them. So for series capacitors, then you had 1 by C, which was equal to 1 by C1 plus 1 by C2 plus 1 by C3. That is what we derived in the short while ago. So that is only that's the difference between resistors and capacitors. So what happens in series for resistors happens for capacitors in parallel, and what happens to resistors in parallel happens to capacitors in series. Okay. Hope this is clear to you. If you're ready, then we will do an example problem. Okay, let's do example problem 2.9. A network of 4 10 microfarad capacitors is connected to a 500 volt supply as shown in figure. So determine A, the equivalent capacitance of the network, and B, the charge on each capacitor. Okay. So there is a note given. Note, the charge on a capacitor is a charge on the plate with higher potential, the positive, okay, equal and opposite to the charge on the plate with lower potential. Okay. So we already discussed that. They have given that as a note, so you can ignore that because you already know it. So this is the network. So you have C1. And then you have C2, and you have C3, and then you have C4, okay, and they are connected to the battery. So this is C1, this is C2, this is C3, and this is C4. Okay, so let's see. So this is the point A and B. This is where the battery is connected, right? So I need to find the effective resistance with respect to these 2 points. Because those 2 are the points where the battery is connected. So my effective capacitance or my effective resistance will be between these 2 points. If you take these 2 points where the battery is connected, you notice that C1, C2 and C3 are in series, and C4 is in parallel to that. So let me find the equivalent for this one. So this will give me, first of all, this will give me this kind of a circuit. First I have C4, and I have this 500 volts. And then I have this effective resistance of C1, 2 and 3. So this is what I have, right? Okay. So what do we know? We also know that the charge on this must be equal to the charge on this because they are in series. For series circuits, the charge must be the same, solid, right? So Q will be here, and then minus Q will be there, and then plus Q will be there because the conductor will become a single conductor. So minus Q will be here, then this will become plus Q, and this will become minus Q. So you get all that, and you have this kind of thing. Okay. So what do we get now? So what do we get? We get we need to calculate C123, right? So 1 by C123 is equal to 1 by C1 plus 1 by C2 plus 1 by C3. But they said all capacitances have equal amount, that is 10 microfarad. So each C is equal to 10 microfarad. That's what is given in the problem. So So this is 1 by C123 is equal to 1 by 10 microfarad plus 1 by 10 microfarad plus 1 by 10 microfarad is 3 by 10 microfarad. So C123 is going to be equal to, okay, C123 is going to be equal to 10 microfarad by 3. Okay, so that is the effective capacitance. So this is equal to 10 by 3 microfarad, and that in parallel with 10 microfarad. Okay, so what is effective resistance? Effective capacitance C is equal to C123, because they connected in parallel. It will become C123 plus C4. So 10 plus 10 by 3 microfarad. So that will be 30 plus 10, 40 by 3 microfarad. So that is the effective capacitance of this circuit. So that is part A. And what is part B? Part B is a charge on each capacitor. Well, that is actually easy, because you see the charge on C1 is the same as the charge on C2 and the same as charge on C3, right? So the battery will put just one Q here, and that's about it. Then the other charges get induced. Notice, well, the moment it puts a plus Q here, then clearly minus Q accumulates here, plus Q automatically gets generated, then minus Q accumulates here, then plus Q automatically gets degenerated because of induction, single conductor activity. So you get this, right? Okay. So this Q is the same for all the capacitors because they are in series, and that would be equal to the charge on this capacitor, right? The charge on this capacitor, because you know that this charge is also the same. So this is also going to be the same Q. Right? Because we said Q is the amount of charge that this battery puts here. So in the effective capacitance also, that is the amount of charge that the battery should put for this. Right? So if I can find the charge on this battery, on this capacitor, then that must be the charge on this capacitor and this capacitor and this capacitor, because they are in series. Okay? So how do I do that? That is simple, right? So what's the potential across this? Potential across this is the same 500 volts, because they are connected to the same 2 points, right? So potential V is 500 volts. So then what should be the Q? So we know that CV is equal to Q. The capacitance here for the series circuit is 10 by 3 microfarad, 10 by 3 into 10 power minus 6 into voltage is 500. Okay. So that must be equal to Q. Okay, this Q. So that gives you what? That gives you so 10, and then you have 100 here. So 10 power 3, 10 power minus 6, you get 10 power minus 3. So 5 by 3 into 10 power minus 3 coulomb. That's a charge on this capacitor, and that's a charge on C1, C2, and C3. So C1, so which is Q1, is equal to Q is this value 5 by 3 into 10 to the 3 minus coulomb. So that would be the charge on C1 and C2 and also on C3. So we are done with the first 3 capacitors, and then you take this capacitor C4. I got 500 volts here, and 10 microfarad here. Then I may have another capacitor, so C4, charge Q4 there. And how do we calculate that? Again, we know that C4 into V is equal to Q4. And C4 into this voltage V must be equal to Q4. So that gives you C4 is 10 to 10 power minus 6 into 500. Okay, so that should give you is 5 into 10 power 3, that gets 10 power minus 6 you have. So you're going to have 5 into 10 power minus 3 coulomb. That is a charge on this capacitor. So you can say that charge on C1, C2 and C3 will be equal to 5 by 3 to 10 power minus 3 coulomb. And then charge on C4, and that is equal to 5 into 10 power minus 3 coulomb. So what's the total charge? This charge plus this charge. So the total charge, I can say Q, which is equal to small q plus Q4. That's the charge which the battery has supplied. Battery supplies to this capacitor and also to this capacitor. And the rest of the charge get induced because they are in series here, right? So Q is Q plus Q4, and that gives you 5 by 3 to 10 power minus 3 plus 5 into 10 power minus 3. So that must be equal to 15 plus 5, 20 by 3, 10 power minus 3. So the total charge Q must be equal to 20 by 3, 10 power minus 3. So we have found the capacitance, the effective capacitance of the whole circuit. Okay, so that is here 40 by 3 microfarad. And then we also found the total charge on all these capacitors will be equal to 20 by total charge coming out of the battery will be equal to 20 by 3 to 10 power minus 3 coulomb. And out of which 10 by 3 coulomb will be on C1, also on C2 and also on C3. And no, okay. 5 by 3 10 power minus 3 coulomb will be on C1, C2, C3. Okay. So 5 by 3 10 power minus 3 coulomb will be on C1, C2 and C3. Sorry about the first statement. And on C4 you will have 5 into 10 power minus 3 coulomb. So together we are going to have 20 by 3 into 10 power minus 3 coulomb. That's the amount of charge that has come out of the battery to reside on the capacitor plates. Hope this is clear to you. So with that, the lesson comes to an end, and let's do the summary of the lesson. Point number 1. Electrostatic force is a conservative force. Work done by an external force equal and opposite to the electrostatic force in bringing a charge Q from a point R to a point P is Q into Vp minus Vr, which is the difference in potential energy of charge Q between the final and initial points. We have done that. 2. Potential at a point is the work done per unit charge by an external agency in bringing a charge from infinity to that point. Potential at a point is arbitrary to within an additive constant, since it's a potential difference between 2 points which is physically significant. If potential at infinity is chosen to be 0, potential at a point with position vector r due to a point charge q placed at the origin is given by Vr is equal to 1 by 4 pi epsilon naught q by r, which is the same as kq by r. Okay, so they're talking about an addition of an additive constant in this. So that is an idea you will understand when you learn integral calculus. Okay, we have not done that here. We have simplified the derivation for you. So that is the reason you are not seeing the additive constant there. But you can you understand that better when you do the integral calculus, the indefinite integrals. Okay, so that is what they mean. But other than that, everything else should make sense to you. V or potential at a position at a point which is odd distance from the origin is equal to kq by r. They have expanded the k as 1 by 4 pi epsilon naught. That's about it. The number 3, the electrostatic potential at a point with position vector r due to a point dipole of dipole moment p placed at the origin is Vr is equal to k p dot r by r squared. Okay, just as we have derived the class. The result is true also for a dipole with charges minus q and q separated by 2a, where r is much greater than a. So number 4, for a charge configuration q1, q2 up till qn with position vectors r1, r2 up till rn, the potential at a point P is given by the superposition principle. V is equal to 1 by 4 pi epsilon naught q1 by r1p plus q2 by r2p plus so on until you get qn by r1p. Derive that. Number 5. An equipotential surface is a surface over which potential has a constant value. Just the potential is the same on all points on the surface. For a point charge, concentric spheres centered at the location of the charge are equipotential surfaces. We've done that. The electric field E at a point is perpendicular to the equipotential surface through the point. E is in the direction of the steepest decrease of potential. That's a point you may note. E, the electric field intensity vector, is in the direction of the steepest decrease of potential. Number 6. Potential energy stored in a system of charges is the work done by an external agency in assembling the charges at their locations. Potential energy of two charges q1, q2 at r1, r2 is given by U is equal to 1 by 4 pi epsilon naught, which is k, to q1, q2 by r1, 2, where r1, 2 is the distance between q1 and q2. Then number 7. The potential energy of a charge q in an external potential Vr is q into Vr. The potential energy of a dipole moment P in a uniform electric field E is minus P dot E. We have derived that. Number 8. Electrostatic field E is 0 in the interior of a conductor, just outside the surface of a charged conductor. E is normal to the surface given by E is equal to sigma by epsilon naught in n vector, which is unit vector, where n vector is a unit vector along the outward normal to the surface and sigma is the surface charge density. Charges in a conductor can reside only at its surface. Potential is constant within and on the surface of a conductor. In a cavity within a conductor with no charges, the electric field is 0. We call it as the Faraday cage. Right? Okay. And number 9. A capacitor is a system of two conductors separated by an insulator. Its capacitance is defined by C is equal to Q by V, where Q and minus Q are the charges on the two conductors and V is the potential difference between them. C is determined purely geometrically by the shapes, sizes and relative positions of the two conductors. The unit of capacitance is farad. 1 farad is equal to 1 coulomb per volt. For a parallel plate capacitor with vacuum between the plates, C, the capacitance, is equal to epsilon naught A by D, where A is the area of each plate and D the separation between them. Number 10. If the medium between the plates of a capacitor is filled with an insulating substance, a dielectric, the electric field due to the charged plates induces a net dipole moment in the dielectric. This effect, called polarization, gives rise to a field in the opposite direction. The net electric field inside the dielectric, and hence the potential difference between the plates is thus reduced. Consequently, the capacitance C increases from its value C0 when there is no medium or vacuum. So C, the new capacitance of the dielectric, is equal to K into C0, where K is the dielectric constant of the insulating substance, or I also told you it is relative permittivity. Number 11. For capacitors in the series combination, the total capacitance C is given by 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. In the parallel combination, the total capacitance C is equal to C1 plus C2 plus C3 plus C4 and so on, where C1, C2 and C3 are individual capacitances. Number 12. The energy U stored in the capacitor of capacitance C with charge Q and voltage V is U is equal to half QV, which is also equal to half CV squared, which is also equal to half Q squared by C. The electric energy density, which is energy per unit volume in a region with electric field, is 1 by 2 epsilon naught into E squared. We derived these two things too. Okay. So the important physical quantities in this lesson are potential, the symbol is phi V, then capacitance C, polarization capital P, which is different from the small p we used for dipole moment. Okay, so small p is for dipole moment, but here we are using capital P. That is also a vector quantity. Then dielectric constant K. We used K, we have used epsilon r, relative permittivity, and dielectric constant are one and the same. So this concludes this lesson. And in the next video, we will start focusing on the exercise problems. Hope the lesson is clear to you. If you have any doubts, any questions, require any clarifications, please get back to me.